anyway, so Dynomite is a distributed key value store modeled after the Dynamo paper. And in my particular case, it's designed to store large objects, right? So one of the things you'll find about all the systems you hear about today is that the original author had a problem they were trying to solve, and you'll see the design decisions made in the project are actually to solve that original problem. So it's sort of interesting how how projects evolve. Like Dynomite's good at storing large objects because I designed it for storing images. So that's what we use it for. We use it to mirror all the images from Wikipedia and all the images from Freebase. It's somewhere very much larger than 6 million, I think, at this point. Then you have the resizes, which we do a number of resizes to insert them into the search results page, and also inside of the republished pages we have for Wikipedia. And then there's metadata for the images. So there's a good amount of stuff in there. Last time I checked, it was somewhere on the order of there's a couple of terabytes. Hello? All right. Yeah, so this is Dynomite at work. This is from Bing Search. So if you go to Bing and search for like a well-known topic, like search for Einstein. If you search for like pretty broad topic names, some of the times at the bottom of the page, a set of answers will show up, and the picture of Einstein that comes from source Freebase, that's all, that is parts of that are served directly from Dynomite. So Dynomite does show up inside of Bing Search, which I think is pretty cool. And currently, you can tell it came from Dynomite because if you click on the source of the image, you'll see the link actually goes to PowerSet's domain, which is pretty sweet. All right, so here's some of the features of Dynomite. We have Merkle tree, a Merkle tree replication protocol. The quorum settings are cluster wide, which is an interesting choice that I wish I didn't make, but it sort of is what it is right now, and it wouldn't be too hard to fix. Huh? Yeah, go right ahead. The cluster wide quorum settings. All right, sorry. So the question was, why do I regret making the quorum settings cluster wide? And the answer is that it's a lot more useful to set the quorum, so the read or the write quorum at the time the request is made. For different clients would have different needs even with the same data. Is basically the idea there. N and Q are a lot harder to set. Oh yeah, N and Q you don't want to set those. That makes no sense. Yes. But anyway, so it uses vector clocks to do the read repairs the exact same way that Gear described it. Dynomite uses a physical token partitioning scheme. So buckets are actually are real buckets on disk that get transferred around when bootstrapping takes place. There's a lot of protocol adapters for talking to the outside world. There's thrift protocol buffers. There's some goofy ASCII one that I came up with. And then, of course, there's binary Erlang. There's BERT if you've been following Tom's work on using binary Erlang term protocol elsewhere. And then there's a pluggable storage backends, and we'll get back to the plugin system because I have some fun ideas there. So, all right. So one of the elephants in the room here is, other than Hadoop, is what happened to Dynomite, right? If anyone was following the project on GitHub, I stopped pushing code sometime in the last summer, and things just sort of petered out, died off, whatever. So here's the real deal. So when Microsoft acquired PowerSet, like a month or so after that happened, I was told, go ahead, push more code up, you're fine, everything's approved. Except I guess I wasn't really approved. Like I don't know, the process is Byzantine and terrible, and the manager who approved it didn't really get real approval or something. But anyway, it came up with one of the lawyer guys, and they said, "Oh, you're pushing code? No, you need to stop that." So I got called out on it, and I haven't been able to push since. So they told me to stop pushing code. I was like, well, you can't stop me from pushing code at home, except my work contributions and home contributions are too tangled at this point to pull out, and I'm not going to re-implement the whole system just to satisfy one of their, this stupid thing that they're doing, especially for something I use at work, right? That's just ridiculous. So there might be some hope for the future. Managers at PowerSet are currently pushing, to get things reopened up because they understand the value in it. So hopefully it'll come together. But anyway, aside from the drama, I've been doing a lot of work on it. So Brad asked asked all the speakers to have sort of use cases and operational experience. So I listened to him a little bit, but not really. So here's the use case and operational experience part of things. What I noticed is that the current version of Dynomite that you see on GitHub, it has a couple of problems. High memory consumption when it's been running for a while. The Merkle trees take entirely too long to update, which was causing backed up sync jobs. So the synchronization protocol would start breaking down. There's like some other nastiness in there. So I've spent the past couple months fixing a lot of these things up, and I'd like to share with you what I did in, I guess, broad terms, since I can't share the code with you. So for the Merkle trees, I actually, when I was at Erlang Factory, I talked to Damian Katz, and he suggested I replace the Merkle trees with CouchDB's B trees. And at first I wrote it off as some crazy idea. Then I looked into it, and I thought, well, these are the perfect data structure for storing this hash tree. So if the CouchDB trees have this incremental MapReduce thing they do, which is pretty much the exact same algorithm that you'd want for making a giant hash tree on disk. So it actually ended up pretty nice. So the Merkle trees in my local branch are now using the CouchDB B trees. They're faster, they're simpler, much smaller memory footprint, and they don't get backed up on writes, which is very nice. The membership system has been completely rewritten. Now it includes actual real-time fault detection to be gossiped around the ring. We have Brad has actually helped out, and before things got shut down, he helped out and wrote a lot of the rack-aware replication stuff, which is really cool. So rack and data center aware replication, where you can have different strategies for saying, like, look, I want this data to be in as many geographically isolated or geographically disparate places as possible, to ensure against hardware failures. So it's pretty cool. And there's also the gossip is not just a wake up and time thing anymore. There's more reactive gossip to get events around the ring faster. And also the bootstrap process has been overhauled. There's now an explicit joining mechanism. So there's a web interface. You tell it what nodes to bring into the cluster. You do it all as one atomic operation so that you don't have this laissez-faire, this sort of laissez-faire way of just put a node in there and let it go and do its thing, because you can end up in weird situations when that happens. Really, honestly, like adding nodes to a cluster it doesn't need to be a hard thing to do, but it needs to be explicit, right? You just don't want to bring up a Dynomite on one machine and have it try to hook up to the cluster when you're just trying to test something, and then half your production data is over here now. That's clearly not a great thing to have happen. So now the bootstrap mechanism, it does online redistribution of data. So while you're serving production requests, your data will be moving from one node to the other in the cluster for rebalancing. The bootstrap process itself is fault tolerant. So if something goes wrong in bootstrap, one of the machines goes down, one of the processes dies, then the old partition map is left in place. So it's an atomic operation. You go from one state of the cluster to the other state of the cluster, or not at all. There's no in-between area where you can fail out. And obviously, it's a no downtime process. There's been some other enhancements that I've made to it. So for the memory consumption in Erlang, hibernating processes seems to help out when they're not in heavy use. There's an Osmos storage engine, which is interesting. So I'm not sure if any of you know, but Osmos is uses sort of a similar data structure to Bigtable, in that it's a log structured merge tree. So it just doesn't have the column store data model tacked onto it. So it's a pure log structured merge tree on disk, and it's very cool, and all in pure Erlang too, which is interesting how you can manage that in a purely functional language. And then there's a lot more introspection functions for remote shelling into the server and seeing what's going on. So, a lot of you are here to figure out what you want to use for your scaling problems. And, in the spirit of full disclosure, you say, well, should I use Dynomite? I am not here to push Dynomite. I don't think you should use Dynomite right now because there's 3 versions of Dynomite. There's the thing that Brad has been working on for Cloudant, which is very, very different from the original. There's the public one, and there is the private one that I have that has so many enhancements. And until this situation gets resolved, I can't in good faith tell you, go out and use Dynomite. So not until Microsoft either opens the dev process back up, or if someone else were to step up to be the maintainer, which would be really nice, that would alleviate a lot of the problems. So if any of you are thinking about wanting a project to work on just for working on its sake, and you know or want to learn Erlang, then come talk to me, and we can maybe set something up. So that is, that's Dynomite. And now I want to co-op things a bit and talk about some ideas I've had for the future of not just Dynomite, but distributed databases in general. To sort of bring it around to some of my wacky ideas. Another show of hands, like how many people have read the Dynamo paper? Yep, awesome. So the thing about the Dynamo paper, and it's really interesting, because you really sort of get this from the Dynamo paper, is that the storage was an afterthought. They made all of these wonderful distribution mechanisms. All the algorithms and data structures they use, the vector clocks, the Merkle trees, the consistent hashing. All of these beautifully designed things, and then it's just like, we'll throw some storage on it, throw a BDB behind it, or throw MySQL behind it, or whatever. It wasn't really, and it actually goes back to the original team that built it, who weren't database guys. They were distributed systems guys. So, excellent distribution, but storage was sort of an afterthought. But let's take that out to its logical extreme. The Dynamo paper really just describes a generic method for distributing state. The fact that it's a database in production at Amazon is incidental to that, right? It's, at its core, it's a very sort of generic system to take stateful things and make them work in an eventually consistent way across a cluster of machines, right? So the question here is, like, why are we even limiting ourselves to building a database with this technology? Well, that's because that's what Amazon did, but I think we could do more. We could do more interesting things. Because we could distribute any stateful service, right? Think about what a database is. A database is just a way of persisting your data to disk. And inevitably, when you have an ORM, you might have an ORM in your web app layer to translate between the relational world and the domain model of your application. But really, when you think about your application, especially if it's a RESTful web application or something like that, your application is actually describing a data model. Your data model is a subset of your domain model, the subset that's being persisted, right? So what if, why isn't your application just a database with application logic, right? And this is sort of some of the ideas that I've thought through to sort of have this proposal for something like a Dynomite framework, or call it Dynamo framework, whatever. It doesn't have to be Dynomite. But the idea is to take any data model and distribute it, clearly within reason, of course. And what can we do with something like that? And so here's some of the use cases I envision. Obviously, you can build databases out of it. Big surprise. You could build a message queue out of it. You could build tuple spaces out of it. Sort of these generic things. But here's the interesting thing. You could put a web application server inside of a Dynomite, which is going to look kind of crazy. So let's go back. It's really nice. Gear showed us their web architecture at Gilt, and so it's a very traditional web architecture. And this is what you typically have. You'll have some sort of load balancer in front of a bunch of stateless app servers who will all talk to maybe a bunch of Memcache instances, And they'll also talk to either a database or a cluster or a database cluster, some sort of thing. But the point here is that you keep all of your app servers stateless, right? And then you've sequestered your state into these big scary things over here. You've taken your state and says, okay, all the state, you stay in this memcache thing here because I don't want to deal with you, or you stay in this database here because we don't want state polluting our app servers. And the reason for that is because it's just really, really hard. It's a hard problem to have the load balancer be smart enough to set to. I mean, you can persist requests based on cookies, but that sucks for its own reasons. But the idea here is that you need to keep state out of your app servers because you're going to need more than one app server, and the load balancer can't really know about the internals of your application enough to route intelligently. But let's say we turn this on its head, right? What if your load balancer was actually Dynomite or something similar, a Dynamo type system? You could have a REST wrapper around it. And then instead of a storage engine, you'd actually have your application server, your web framework running inside of Dynomite, talking to local disk, talking to local memory cache, with the guarantee that that resources identified by the same key will always go to the same app servers. Therefore, you can consistently, you can predict like how the state will affect each app server, and then requests for the same resource will go to the same one. So we come back to this idea that your data model is actually what you build into your app. It's it's application specific. Your data model could be a blog. Your data model could be a CRM. Your data model could be a parts store, a car parts store. It really doesn't matter. A REST app is just a stateful service for exposing operations on your resources, which describe your data model. So one of the advantages of having a system like this is you'd have lower latency because there's less hops to get to your data. You don't have to go to a database server. Your app server is its own database server. This is just having your application logic live inside of the database. You don't have to have a stateless app server, so you could do all sorts of goofy stuff and have state inside of your app server. And you wouldn't even, you could throw away all these old assumptions about what you can't do inside of an app server to get your work done. You could have a hyperlocal cache because your app server could actually just put stuff in local memory, and because the request would persist to the same app servers, it would be served from the same piece of memory. And you could also tune your app's 99th percentile directly, right? So if your latency is too high, your 99th percentile latency is too high, just change the quorum constants. And it's interesting when you think about it, because then you can have an app server, and two app servers could be doing the same job, and the first one to get a result back wins, right? And when that happens, you're going to duplicate a little bit of work. But inevitably, your client, your user on the other end of the web gets to see his page a little bit faster. So that trade-off might be worth it to you in aggregate. So there's some of the advantages of having a system like that, and the disadvantage, obviously, it'll only work with REST apps, right? Because if you think about it, so if you think about having the application server bubble up data from its local database. Clearly, you need to have some identifier, because we're just still talking about key value lookups here, right? Just in a different way. So so obviously, to have a web application built around key value lookups, it really needs to be a real REST service. In the fact that a single resource identifier identifies a single resource or a collection of resources, so that these requests can get persisted to the same machines, and you can be sure that they're going to have the data. And then you just turn, post or put requests into write requests, and HTTP get requests into read requests. But it would have to be a REST app. You couldn't have like other goofy operations built on top of it that don't identify with a key or a value. Read repair would be non-trivial for some applications, and just downright wrong for things like financial info, right? Clearly, you don't want eventual consistency when you're talking about someone's credit card or the amount of money in their account. But and the read repair would basically be you'd take the structured data from both of your app servers, and then run it through your presentation layer. So if you think about Rails, your controller would bubble up this structured data for this resource. It would run it. It would do its read repair on it. Do the eventual consistency thing and build a consistent model of this resource, and then run it through the presentation layer to turn it into HTML, JSON, XML, or however you're delivering the resource to the client. But then that would be a non-trivial thing to do, but I think it's doable for a lot of applications. And obviously work gets duplicated. So this would be something where you couldn't really do it with applications that do a lot of background jobs, right? Without a lot of coordination between the nodes to make sure that these long-running, expensive background jobs don't get done twice, unless that's actually what you want. So what would these stateful services be responsible for in this world? You're talking about an API, talking about a framework. What does that mean? So the responsibility of the services, they persist their data however they want to, or not persist it, whatever the case may be. It'll run queries, do operations locally within its own domain. Wouldn't even have to know that there's other instances running out there. And then just provide these read repair functions to put the data back together when it's being read back out. It could provide its own hashing scheme if it wanted to, and it publishes its API to Dynomite. And Dynomite would be responsible for basically all the routing, handling node membership, being the network interface to the outside world, versioning the data. And also, it would really be responsible for failure detection. Think about a load balancer that knows instantaneously when one of its nodes is acting up. You wouldn't have a dropped request because another node would pick up that request and it would just go with it, which is pretty cool. So there would have to be some sort of API negotiation where your storage engine or stateful service or whatever you want to call it, your app server, publishes its own API. What can this do? What are my data types? How do I do my conflict resolution? How do I collate like multiple results if we're doing list type queries? And what are my partitioning strategies? And the client protocol would be negotiated. And the client protocol will be something that Dynomite bubbles up from that negotiation for the outside world. And then you could stick like a REST wrapper in front of this, and then boom, you have this RESTful service now. Or you could just use the raw Dynomite protocol. It really wouldn't matter. So that's sort of the size of things. So it's a wacky idea, but everyone's talking about big data, but we all still think of it as like the database has to live over here. We have to keep the data separate from the app servers. We have to keep these things stateless. I think it's a much more interesting idea to say, why do we have to do that? Why can't we bake the app data into the database? And you might think, well, you're talking about stored procedures now. Yeah, but that in a way that doesn't suck, in a way that you can distribute across many machines, or just you could put something else behind it too. It doesn't even have to be an app server. That's an interesting thing. So if these sound like cool things you want to work on, then I'd love for any of you to take over the Dynomite project. So here's the links on GitHub. The wiki's up there, which has a longer version of this idea on there. That's my Twitter username, and I'm also that on IRC. So let's take some questions. I think Brad's coming back with the mic.
We'll see if you really exploded everybody's head with that.
Or it was just babbling, clicks and whistles, right?
I know that at PowerSet they use, I guess Microsoft now, but they use both HBase and Dynomite. What's the experiences and kind of the use cases for each thing?
Right. Well, HBase really. So when I first started, so HBase is something that you could actually use for this use case now. With the 020 release, it's much better for serving live traffic now. But when I originally looked at it to solve this, because I looked at it to solve this problem, and it just simply wasn't ready at the time, and I needed something like yesterday, to solve this problem. So in true not invented here fashion, I hauled off and wrote a Dynamo clone. To my credit, though, there were no other public ones at the time. So
think you cooked them.
All right. All right, well, I mean, if anyone has questions later, you can find me on the IRC room or just walking around. Yeah? Oh. I have not.
Repeat the question.
Have I read, I'm sorry, what was the name? Pat Hellen's paper on. Really? That's awesome. Awesome. Yeah, I would love to read that. At least someone who's thought through this a little bit better than I have. That'd be nice. Anything else? All right.